Oh, hello. Yeah, good evening, sir. Yeah, this is Arvind Prajapati, sir.
Yeah,
Uh,
Arvind.
sir. Yeah. So, thank you, sir, for giving your valuable time and joining the session, sir. And our participants will still joining, sir. So, we will start at sharp 2 p.m., sir.
Yeah. How many
Uh,
of them are
so,
there?
after, sir, 68 participants are there, sir.
68 participants. What is
And
the distribution? Are they all faculty
uh,
members or
sir,
PhD?
like, yeah, yeah, more than 50 are like faculty, sir, and 10 are PhD and MTech, sir. PhD and other industry persons, sir.
Okay, okay. So
Uh,
you are
sir, and yes, sir, after your session, sir, immediately we will start validatory function also, sir.
okay.
Uh,
No issue.
okay, sir.
No issue. So how
In the same meeting, sir. In the same
same
session.
link?
Yes, sir. In the same meeting, sir.
Okay,
Sir, yes,
okay,
sir. Means you don't have to leave that meeting, sir. In that meeting, we will start, sir.
okay.
So, sir, how much time approximately you will take, sir? 2 hours or 1.5, 1 point means 1.5 hours, sir, approximately, sir. Can you just tell so that we will inform others?
No, let us
Okay.
start. See, your slot is 2 to 4, correct?
Yes, sir. Yes, sir. Yes, sir.
Okay, so your valedictory you start at 4.
Sir. It will start 4, sir. If you will finish early, then it will start early. Otherwise, 4 p.m. I have
No.
informed other persons, sir.
Now, please start at 4 as per the schedule.
Okay, sir. Okay, sir.
Well,
Thank you
I
so
will
much, sir.
ensure that I will not cross that time limit.
Okay,
Fine.
sir. Okay, sir. Okay,
Whatever
sir.
I
Okay,
want
sir.
to say, I will say it prior to that only. Okay.
Okay, sir. Okay. Thank you. Thank you so much, sir. Yes,
Okay.
sir.
Okay.
So, sir, just 2 minutes, sir. After that, we will start, sir. Thank you, sir.
Sure. Okay. Arvind. Just signal me.
Good afternoon, everyone. I welcome you all to this session. It's my pleasure to introduce Professor Vinay Krishna Roy, Professor in Department of Electrical Engineering and an IT Researcher. Professor Roy has more than 35 years of experience in teaching and research. He completed his BE from REC Silchar and his MTech and PhD from IIT Kharagpur. He has published over 150 research papers and guided several PhD and MTech students. His main research area includes control system, smart grids, chaos theories, and AI application in energy systems. Today, he will deliver a talk on fault detection, isolation, and accommodation technique in dynamical systems. Now, I warmly invite Professor Vinay Krishna Roy to begin his talk.
Yeah, thank you for this introduction. I welcome all the participants here and hope the others will join.
Yes, sir.
So let me share my screen, see if it is visible.
Yes, sir. Yes, sir. Your screen is visible, sir.
Screen is visible. So as it says, I will be talking something. Am I audible also?
Yes, sir. You are audible, sir.
Yeah.
Yes,
So if there is any issue, you please call me back, because if it get cut or anything, please call me back in my mobile. Fine.
Okay, sir.
Okay. So as you see it here, we have a very general topic: fault detection, isolation, accommodation techniques in dynamical system. In fact, uh, in our institute, we have control and industrial automation as a MTech program, where we teach a subject on this. So basically, you understand what I'm trying to say is a subject content. So therefore, I will summarize the whole thing, and I'll try to speak something that you get an overall view of it. Fine. So therefore, what are set as an expected outcomes? This is very first of all, we will ask the question to ourselves: why this fault detection, isolation, diagnosis, accommodation at all? Do you really need this? Fine. So that's the first question that we'll try to understand. And then again, understand the complete, fault detection, isolation, diagnosis, accommodation framework. What is this fault? What is this failure? What is the detection? All this. Then we will talk about, basically there are two approaches in the whole gamut. There are two approaches. One approach is what you call hardware redundancy based approaches. And there is another one, what you call the analytical redundancy based approaches. So we will talk about both of them to understand how it goes. Then we will try to end, by taking some real life examples that will give us some kind of feelings. And in many cases, what happened, many cases we do our algorithms, but we are caution. What is the caution? Steel industry is dominated by PID. Still, more than 85% industries are using the PID controller, even though we as a control engineer have been, designing our sophisticated controller, robust, adaptive, and whatnot. Fine. But here you will find that industry is accepting this notion, and industry is implementing this concept of fault detection diagnosis so that it saves them. So you will just take some real example that will give us some kind of feelings. Fine. So this is the flow of presentation. Now let us start with the strong introduction and motivation. Before I start and jump to the topic, I will just do the quiz, or rather I will take a poll from you in this mentimeter.com to understand how many of you are really acquainted with this particular subject of fault detection, diagnosis, and accommodation. Fine. So what I'll do is I will go here. This is my Mentimeter. I Whether my screen is visible to you?
Yes, sir. Screen is
Yes,
visible,
sir.
sir.
Yes, sir.
Yeah. So you please, whether you are in laptop, you are in mobile, please go to this menti.com and please use, this is the code 17515934. This is the code as you see it here. So I just left few questions. There are 3 questions. The first question is, are you familiar with fault detection diagnosis of dynamical system? No, yes, in low level, yes, in medium level, yes, in high level. So this is the first question. Then your second question is, how are fault and failure related? Right? So answer for option 1 is they are the same. A fault causes a failure causes a fault. There is no relation between them. And the last question here is, how are fault isolation and fault diagnosis are connected? Right? A fault isolation is a subset of fault diagnosis. No connection between them. Both are the same. A fault diagnosis is a subset of fault isolation. Yes, please. I don't see your response here.
Doing, sir.
Please join to menti.com and use this particular code and try to respond. Mhm. What about others? Yeah, I could see only 4 of you have joined so far. I'll just spend another 1 minute and then we'll go. Okay, let us go back. Let us go back. Fine. So what we understand here, is are you familiar? At least I got some response where they are saying familiar in medium level. Good. Next is fault and failure, how they are related. You are saying there is no response here. Then we have got how fault isolation and fault diagnosis are connected. There's a mixed response that I could see it here. Okay, so let us go back. So okay. Okay. So let me proceed now. Okay. So topic what is given here that says fault detection and isolation accommodation, but later on, just after a few slides, we will basically add here in place of isolation, we will bring the word diagnosis, and we will see isolation is a subset of diagnosis, right? Now, first thing is what is the fault, fine? Now, fault, as we all understand, it's an abnormal condition or defect in a dynamic system. What happens if there is a fault? It causes to deviate from its normal behavior, fine? Now, if there is a fault, what happens then? If we do not take care of this fault, it leads to a failure. It leads to a failure. So what is failure then? A complete or significant loss of functionality of the dynamical system, fine? Now, if you see them in a comparative way, then in comparative way will be abnormal condition or partial deviation. In case of failure, it is complete loss of functionality, fine? What happened even with a fault, system operates, but it operates in a suboptimality. What happened in case of failure? The system stops and severely degrades. Detection, observable via monitoring, fine, and this is failure is often observed or detected when that system stop functioning. So its system comes to a halt. Example, you have a misaligned valve in a process plant is still working, but it is suboptimally working because of your misaligned valve. Pump breakdown in a water system. Once pump is no more, then there is no other way to continue with that water system, fine? The management, how do you do it? This is it can be managed. This is what you call fault accommodation or fault tolerant. Both are synonyms. And in case of failure, we have no other option but to go for repair or replacement, fine? Okay. Now, this kind of, I'm so happy that there are a few industrial participants also. For them, it's very common scenario, in any process plant, you will find a very big room where from you see, monitor all the functioning of the plant, fine? So this is something which gives us whether our systems are acting in a normal manner or there are some fault which got detected, right? Now, after understanding the difference between fault and failure, as we have said, whenever it's deviate from its normal operation, this is due to a fault. If we do not take care of that fault then and then, this particular fault gradually increase and finally lead to a failure of the system, which basically halt the system, fine? Now, question is, how do you detect that fault? So what is the first process? First process is fault detection. So what is this process? This is the process of identifying. This is the process of identifying. This is the process of identifying the presence of abnormality, right? So this is the process. This is the process of identifying the presence of abnormality. Now, so far as theory is concerned, practically it is also not very tough so far as detection is concerned. But we will see that next we will talk about something called isolation, something called diagnosis. That is basically the toughest part of it. Now, what is an example? In manufacturing, sensor detect irregular vibration in machinery, fine? So you have some sensors which detect some irregular vibration, but still your machine is running and it has created some kind of alert, fine? Some kind of alert that there's a fault in the system. This is your fault. What is fault isolation? Fault isolation is also known as fault localization. determine the specific location or the component where that fault has occurred. Fine. So this is the location that we are talking about. Now, once you go to fault diagnosis, it basically identifies the type, magnitude, root cause of the fault in a dynamical systems. Fine. So therefore, once you do the diagnosis, it not only gives in which component, that is the location, but also tells you what exactly had happened, what are the cause for it. So that's your diagnosis. So we will consider diagnosis is a superset of isolation. Isolation is a subset. With this particular background, what we'll do is we will basically drop the notion fault detection, isolation, and accommodation by fault detection, diagnosis, and accommodation. With this explanation that isolation is a subset of diagnosis. Fault accommodation, which is also known as fault tolerant control. What happens? There is a fault in the system. I do something in the system so that my plant continues to run. Obviously, it cannot run with its full capacity, but with a sub capacity, it continues to run. Fine. In power plant, redundant pumps activate to accommodate a failed coolant system, ensuring continuous energy productions. Fine. This is your fault accommodations. Fault accommodation, so far as fault accommodation is concerned, once we will understand the hardware redundancy, then we'll understand in case of hardware redundancy, fault accommodation is being designed in a very simple way so that you get a lot of fault accommodation there. Right? Okay. Now, if we try to see them, what they are, fault detection, isolation, diagnosis, and accommodation. They are basically detection. It is focuses only whether fault is there or not, yes or no. And fault isolation is basically talk about what are the locations of fault. And fault diagnosis, it goes inside type, size, cause, etc., etc. And then this is fault accommodation is even with this fault in the system, can you adapt the system to go ahead? Fine. So can I adapt that particular fault in the system? Can I accommodate that fault in my system and I go ahead? Okay. Now, what are the methods? Methods are basically sensor monitoring, residual analysis. This is what we do for fault detection. Then we will talk about false isolation is fault signatures, observer bank. These are used for isolation. Then a lot of algorithms are used for fault diagnosis, reconfiguration, and redundancy. What I was talking about, hardware redundancy, are used for hardware. This is fault accommodations. Right? Now, what is real life impact? Real life impact, if there is a fault, RD alert industrial automations is helpful because it helps us to go to a failure stage. Number one, it basically saves the whole plant from a great loss. Fault isolation. So once you isolate something that happened there, so you have already identified which component needs to be repaired. If you have a provision of redundancy, you use that redundancy channel when the plant will be not in operation, then or you isolate that particular portion and basically repair that particular identified component. Right? And what is fault diagnosis is not only diagnose that a fault had happened, but there is something called prognosis, where basically you monitor the health of the system. And by monitoring the health of the system, you can plan your preventive maintenance to save your plan from any fault. And what is fault accommodation? If you can accommodate your fault, it will give you an uninterrupted operation of critical infrastructures. Fine. So this is the overall scenario of all this. Now, question is why fault detection, isolation, accommodation, or why fault detection, diagnosis, accommodation? First thing is It's not that it was not there in earlier processes. It was also there in earlier processes, but what had happened over time, our processes are becoming complex and complex. For example, I have a self-driving car. Fine. Now, in that self-driving car, suppose there is a failure in this, there is a sensor failure in an autonomous vehicle. Fine. There is a sensor failure in the autonomous. Maybe a malfunction in the LiDAR unit, which basically measure the distance. Fine. And miscalibrated camera, which is giving you the 3D view of your car where it is passing. It is a miscalibrated. What is a miscalibrated? Something what you see as 5 meter distance, actually in 1 meter distance. So miscalibrated. So what will be the consequences? Consequences will be you will meet with an accident. So therefore, I have these are some some YouTube videos so that we can have some kind of feelings about it. But I understand I cannot go to those. Fine. So I will try to skip this. Yes, I'm trying to say you why we are so interested, why we all feel the need of fault detection, diagnosis, and accommodation. Fine. So therefore, we will possibly never use a self-driving car which made an accident. Fine. So car accident is our accident. So we will never use. So therefore, we should take utmost caution, care that all sensors and devices which have been used in that self-driving car are working perfectly. Fine. Now, again, what we want that if there is any fault or failure in any of them, there must be something which will take me, maybe my speed will get reduced. Initially, it was driving at a speed of 60 km per hour. Now it will drive at a speed of 30 km per hour, whatever it may be, but it will at least help me to come to my destination. So it will have that accommodation facility also. Right? That is why. Now, this is a scenario. This is a scenario that we often see. In Indian road, you see the electrical car catches fire. And in most of the cases, you find that battery got heated up, and basically that is the cause for these particular catching fire of the vehicle. Fine. So what is the major cause? Major cause is thermal runaway in that lithium-ion battery. Fine. So therefore, what is the solution? Solution is nowadays they are talking about intelligent battery. They are talking about smart battery. They are talking about battery management system so that all these can be detected and avoided. Fine. So therefore, this gives another very practical example where we feel we require FDDA. Now, why do you require this? Let me go back to this. I hope all of you here, you all remember that 2012 blackout on 30th and 31st July. Fine. Whole North India, they were in dark. This was a cascaded effect. Fine. And those who are working in this particular area, they know during that time, possibly there was only one PMU. But after this particular incident, now we have plenties of PMUs which are giving us real-time information about the status of our system. So therefore, we never wish that we will reoccur this kind of scenario in India. Fine. So therefore, we require, even if there is any fault, immediately that should be detected, that should be diagnosed, and that should be isolated. Fine. That fault should be accommodated. Aerospace industry, this is life critical industry. So therefore, in this life critical industry, we will see that redundancies are mostly in hardware redundancies. Fine. So what happened here, instead of one particular engine, there may be two engines. In place of one particular sensors, there may be three sensors, and we use some kind of voting logic. We will talk about it. Fine. Now, this particular YouTube, which I have notated here, will take us very recent Ahmedabad case. Fine. Although we do not know now what exactly was the cause for it, but one thing is very sure, that fault detection diagnosis is there. A FDDA is there, and it is there in this life critical industries for last many years. But that particular things has not worked. That has causes that fatal accident. So therefore, we definitely do not want reoccurrence of this. Therefore, we need an effective FDDA. Fine. Now, in industrial robot, fine. These robotics manipulators are used for precise and repeating tasks. Fine. Now, if you see, let me go here and show you how series of robots how
Industrial and collaborative robots are taking over manufacturing at an unprecedented rate. The International Federation of Robotics has predicted that nearly 2 million new robots will be installed in industrial settings by the end. Hi, everyone. My name is Ashley Elsasser. Today,
is it visible to you?
Yes, sir. Yes, sir.
Excuse me.
Yes, sir. It is visible, sir.
Hello.
Yes, sir. It is visible, sir.
Arvind.
Hello. Am I audible? Hello.
Yeah, you are audible. Yes,
It is visible, sir.
I cannot hear.
हाँ सर, it is visible.
Arvind.
हाँ सर.
Hello.
हाँ सर. Yeah, your screen is visible, sir. Okay.
Am I audible?
हाँ sir, you are audible, sir.
Hello.
हाँ sir. Yeah. Hello. हाँ sir. We can listen you, sir.
Hello.
हाँ
Hello.
sir. Yeah.
So
I'm
call
not getting
him.
any response. I don't know what happened. At my end, seems to me things are fine. अभी हमको रिस्पॉन्स नहीं आ रहा है वहां से. हमारा आवाज आ रहा है क्या? हाँ. हाँ, कोई जवाब नहीं आ रहा है. कोई जवाब नहीं आ रहा. So it seems, am I audible to you?
Yes, sir. Yes, sir. You are audible, sir.
Saran? Any of
हाँ
you can
actually.
unmute yourself? Please let me know, am I audible to you?
Yes sir, you are audible, sir. We can listen you. हाँ.
Okay.
हाँ sir.
Okay, audible. Someone has said. Okay. So we were somewhere here. Fine. We talked about aerospace, and then we were talking about this industrial robot. Fine. What I was basically trying to show here was, please check.
Industrial and collaborative robots are taking over many.
Now just look at this picture.
Today, I will be exploring the differences between traditional industrial robots and collaborative robots. We'll look at installation requirements for each type of robot, common applications, and implementation options. Where they excel in painting and welding, heavy-duty application, and collaborative. You decide the best automation factory automation standard for decades. Heavy-duty applications space requirement, greater investment, machine builder to make your project successful.
Okay.
Hi everyone, my name is Ashley. We'll look at installation requirements, all with the goal of helping.
I was searching for a particular picture.
You may know them. Applications like a high degree of programming expertise.
Okay. So I was basically searching for that particular, picture where it shows so many robot, so many, this is robotic arms, they are doing simultaneously in a synchronized manner, fine, in a production line. So if there is a mistake, there's a fault in any one of them, what will happen is whole process will get wrong. So if the product that whole batch will become a faulty batch product. Fine. So therefore, this kind of fault detection is so important there, right? Now, in our scenario, what would happen? See, this is an Pune automatic stamping and assemblies. Fine, in Pune, what would happen is one particular robot was there, and this particular robot has malfunctioned, and as a result, it has killed one of the worker. In this particular incident is of February 2021. So therefore, what it suggests that necessary fault detection, diagnosis things were not there. That particular precaution part was not there. So therefore, this also tells us that we must have this fault detection, diagnosis, and accommodation. Right? So finally, if we sum up whatever we have seen, what is the summary? We desire a strong resilience of our power system even after a strong storm. Fine. That is your basically, that grid resilience, what you have talked about. Fine. So who will be in the background? In the background, there has to be some fault detection, diagnosis, and accommodation. Fine. Next, we wish our self-driving car reaches its destination without any accident. Fine. We safely use our EV car without any fear of system fault or contribute our share in reducing in carbon footprint or carbon emission. Fine. We do not want a repetition of India's largest electrical blackout, a two-day event on July 30th and 31st in 2012, which affected over 620 million people across northern, eastern, and northern India due to cascading grid failure. We do not want a repetition of that. We all pray for a safe air journey and not to see a reoccurrence of the incident of Ahmedabad air flight. Industrial automation is unavoidable. Fine. So would have to do it, but not at the cost of human safety and security. So therefore, this is unavoidable, but this industrial automation must come with safety of human, security of human, security of environment, and therefore we require fault detection, diagnosis, and accommodation. Therefore, fault detection, diagnosis, and accommodation is a must in today's industrial automation scenario. Now, if you see few examples, worldwide, that how this fault detection diagnosis has helped us. UK National Grid Insulator Fault Diagnosis. This is an incident of 2019 due to a storm event. Fine. Now, let us not go here. Let us not go to detection and diagnosis. So somehow they have done the detection and diagnosis. What you see it here, accommodation involves switching to parallel feeders, deploying mobile generator, restoring 90% power within hours via automated topology reconfiguration. Fine. So this is what is that power of that accommodation. Okay. Now, as we have said, that fault isolation and fault diagnosis, they are connected. Fault diagnosis is a superset of fault isolation. Fine. So we will move forward with something fault detection, diagnosis, and accommodation instead of fault detection, isolation, and accommodation. Now, if there is any questions on whatever we have said, we have tried to basically give a feel. What is this fault detection, diagnosis, isolation, accommodation? And then why really you want it? Why you want it? And another thing, what has been emphasized, that although whatever we do in our theoretical class, in our theoretical laboratory, whatever paper we write, fine, whatever papers we write, most of this paper remain in its theoretical domain. There is no taker in the industry, but this is an area where industry has applied many of the findings in theoretical domain. So this is an area where most of the theoretical findings are being implemented in industry. Hardware redundancy and voting logic. So this is the, what is this hardware redundancy? Hardware redundancy involves duplicating critical component in dynamical systems. What we have got two types of redundancy. One called passive redundancy, one called active redundancy. What is passive redundancy? I have a parallel duplicate component, but that is not in use. That is not in use. I will use it as soon as I see there's a failure, there's a fault in. Right? But in active redundancy, all these components are being simultaneously operated, and then you use some kind of logic that whether any of them has become faulty. If not, that a non-faulty one or the correct one is being used in your operations. You require only one. So therefore you get through one channel only, but at the output you check whether all these are faulty or any of them have become faulty or all of them. So this is this is the most common configuration which has been used. Triple modular redundancy, where three identical modular process the same input and output is determined by consensus. What we have here, we have same sensors or the same actuators which excited by the same input. What is ideally all three should give the same output if these are all perfect. Fine. So there is a checking here whether they are giving, all three are giving the same results. If all three are giving the same result, you take the output from any one of them and you continue your plant. But if anyone, if they are not, then what we check, we go for a kind of voting. What is that voting? We find that out of 3, how many readings are matching. So if we find the reading from 1 and 2 are matching, but 3 is not matching with the reading of 1 and 2, then we presume that 1 and 2 are not faulty and 3 has gone faulty. 3 has become faulty. Fine. This is our presumption using the voting logic, and because the probability that 2 of them will simultaneously become faulty is very less than 1 of them becoming faulty. So this is our voting logic, which has been used in most life critical plants, life critical devices. Hardware redundancy and voting logic, you can see aviation in all our plane, Boeing 777, triple redundant flight control computer, use voting to handle sensor actuator faults, ensuring safe flight. Then if you see spacecraft, NASA, Ariane, what redundant system. So therefore they are not only 3, they have got 4 redundant system with adapting voting to accommodate radiation-induced error in deep space. Fine. In petrochemical refining processes, while continuous operation of pump valve and distillation columns is essential, they want this plant should run continuously. Redundant power supplies and UPS prevents blackout from causing hazardous shutdown. So therefore, they give redundant power supply to it. If anything happened to our primary power supply, there will be immediately backup supply. There will be immediately the UPS is there, and from the UPS it will take up by the backup power supply. Fine. In automotive industry manufacturing, robot assembly lines for welding and painting require precise synchronization. I was trying to show you that particular picture, which I could not. Painting require precise synchronization to avoid defect or halt. Now, this Siemens PLC, they uses redundant CPU and IO module to provide failover over controlling conveyor belts and robots. So therefore, what you see it here, that to avoid a whole batch product loss because of not producing the standard product because of some faults. So they use some redundant CPUs and IO modules. Now we will come after realizing that fault detection, diagnosis, and accommodations are essential. Industrial automation today cannot be succeeded without an effective fault FDDA. Therefore, let us see it here, how different approaches are classified. Right? Now, fault detection approaches are classified mostly. They call it model-based fault, data-based fault detection diagnosis, knowledge-based fault detection diagnosis, and hybrid fault detection diagnosis. So here we will mostly concentrate on model-based. We'll mostly concentrate here on model-based. Fine. Data-based, knowledge-based are also used. This knowledge-based is used in many places. For example, in agriculture, there are now number of expert system or expert software. Once you give an image of your crop, immediately it will do the analysis and immediately it will tell you if that your crops is suffering from any kind of diseases, etc., etc. Fine. And these are mostly run with if-then rules. Fine. Even in medical science also, there are knowledge-based expert software. Fine. So these are all used to. Data-based Data-based, what happened here is, anyway, we will go through one by one. Yep. So in our subsequent, we will try to understand all of them, and then we will concentrate mostly on model-based FDD. This classification is done based on the criteria. What is their foundation? In model-based, we require a model of the system. In data-based, we require the data pattern. So I need to collect the data from any source. Let it be data from acoustic, let it be data from the sensors, etc. So we have expert rule in the knowledge-based and mix of all of them and hybrid. As usual, as you expect, now the current trend is that we use the hybrid FDD. Data dependency, does it require extensive sensor data? If it requires extensive sensor data, then you go for data-based. Minimal data with a model, you go for model-based or knowledge-based. Fault type coverage, are you covering a known fault? Then you go for model-based analysis or what you call signature-based analysis. For a particular kind of fault, we have a particular signature. That is a particular pattern, right? And if I have some unknown faults, then we will go for data-based analysis. Implementation complexity, model-based needs modeling. Modeling may not be a perfect model in all cases, but if we go for data-based, you require only the data. So after all, you have the sensors, which is providing you data, and you require the computing power, right? And so far as knowledge-based is concerned, so knowledge-based, it requires your expertise on that subject, fine? Now, in model-based, what happened? It relies on a model, a mathematical or physical model of the system. Normal behavior, okay, model-based. There cannot be called physical model. Huh? Okay, so it relies on mathematical model of the system to predict normal behavior, right? Comparing it with the real-time measurement to detect and diagnose fault via residual or parameter deviations. This is what is called model-based. So we will talk about, how do you generate your residual, how do you do, this is parameter estimation based. So this all we'll talk about. What is the example? Boeing 777 flight control system uses Leuenberger observer to detect actuator faults. Fine. Power grid frequency drop analysis is done by state estimation. Right. Now, data-based fault detection diagnosis. Now, what it does, I have n number of data. I do statistical analysis, or I use a machine learning technique. What I do, if these data are representing the normal behavior, it gives me some kind of properties. When they are not behaving normally, they will give me some deviation from the normal behavior. So therefore, I use this statistical measure or my machine learning tools to find out whether my data are showing me a normal data or these data are coming out from an abnormal. For example, vibration-based fault detection diagnosis in wind turbine using deep learning for blade imbalance. Thermal imaging FDD for switch gear overheating using convolution neural networks. Acoustic-based fault detection diagnosis for engine misfire in Tesla vehicles. These are all in use. Fine. These are all database approaches which are used in the real domain. Knowledge-based, employs expert knowledge, rule-based systems or fuzzy logic to detect, diagnose fault, often integrating human experience with system data. Right? What are the examples? Examples is fault diagnosis in nuclear plants using rule-based system for valve failures. Fuzzy logics for HBSS system fault detection based on temperature threshold. Fine. So these are your knowledge based. Now what is hybrid? Combine elements of model-based, data-based, and knowledge-based approaches to leverage their strength, often using data fusion or multi-method integrations. So this is what is your hybrid. I take the advantages of all the three, and then I go ahead, which is become suitable for my requirement. Now we have the chemical process monitoring using model-based parity equation, parity with data-driven PCA. So what is being used here, we will just see that there is something called parity relation. It will come under this model-based, and with a data-driven principal component analysis. So these two are being combined to do chemical process monitoring. Multi-sensor fault detection diagnosis is autonomous vehicle, combining thermal and acoustic data with model-based validation. So we have the model-based, and also we are getting from thermal imaging, and also we are getting acoustic data. So this is data-based and model-based, they are combined, and then we are doing FDD for an autonomous vehicle. Okay. Now let us see parity space approach. Any questions from any of you?
Yes, participants, if you are having any questions till now, then you can ask, answer. And if you don't have, then sir will continue.
Any questions from any of you?
Sir, I think no one is having questions, sir. They are listening and they are
Kiran,
getting.
I'm not audible to you.
Yeah, you are audible, sir. I can hear you, sir. Sir, I think no one is having questions, sir. So you may continue, sir. Sir, you are audible. You are audible, sir. Sir, you are audible, sir.
Hello.
Sir, you are audible, sir.
Yeah, now I'm audible. Please tell me.
Sir, I think no one is having doubts, sir. You may continue. Continue, sir.
Okay.
So one
Okay.
hello.
Yeah, please tell me. Please tell me.
Yeah, the redundant element should be how the number of redundant elements should be decided. It is fixed, or means you have told that there are 3 redundant elements in some system. So is there any mathematical way to decide the number of redundant element?
No, actually, generally what happen, generally we go for 3 elements, generally. Fine. The question is why? What is the logic for 3? Why not 2 or why not 4? Right. First of all, why not 4? Answer is, for example, these are used in aeroplane. Fine. So it not only increases the cost can be compensated, but it takes space. So I need to do everything in a limited space, and therefore there is a constraint on the space, and therefore they basically go for 3. Now question is why 3, why not 2? 3 is because they go for voting logic. And what is that voting logic? Out of 3, it is being presumed that if there is a fault cannot occur in 2 of them simultaneously. But if I use 2, and if these 2 are not matching each other, the result of these 2 is not matching each other, I will be in dilemma. Which one is correct? Which one is basically non-faulty? So therefore, I use 3 and I check the output of all 3. Whenever I find one of them is not matching from other 2, then I presume the one which is not matches with the other 2 is faulty. So that is the logic why they go for basically 3. In fact, in this is Boeing, all these, there are 3 redundant sensors. Fine, there are 3 redundant sensors. And the another one that I have said, NASA, that is their spacecraft which is taking the people to moon. They are talking about the 4 quad redundant. Fine, there are four the same set, same things are in 4. Fine. So these are all used in safe critical systems. Is my answer? You got it? Why it is 3? Is it fine?
Yes, sir. Yeah,
Okay.
yeah. Okay.
Okay. Now, actually, we talked about hardware redundancy. Fine. What you require? You require the hardware components. Fine. And what happened to those hardware components? See, every component has a it's a lifespan. Every component has a lifespan. Now, when you use them as active redundancy, what is that active redundancy? Active redundancy is you use all of them operational simultaneously. Fine. So therefore, if lifespan is 3 years, after 3 years, whether you have actually used them or not, you have to throw them, you have to replace it. Fine. So it involves cost. All right. And again, what I said, not only cost, in some places, basically space requirement has become a big issue. Fine. So there, even for that, you may not be able to basically go for what you call hardware redundancy. Now, what is the importance we have seen? So therefore, we must have it. But is there any alternative of hardware redundancy? So then that alternative is called it analytical redundancy. This is your analytical redundancy. Fine. This is your analytical redundancy. So what I'm doing now, I am doing some kind of redundancy. But this redundancy is not in a physical mode. It is an analytical mode. I have done a lot of analysis. I have done a lot of mathematics. And after those mathematics, it has come this way. Fine. So here, these are basically all coming under that model-based. These are all coming under that model-based. So in the model-based, the first approach, which I'll talk about, is the parity space approach. Fine. Now, let me take this representation of any plant. This is our usual representation. X dot equals to AXT plus BU plus of KFT. So this is a process fault. And Y is equals to CXT plus of FST. So FS is my sensor faults. Right? Now, when there is no fault, and please see it here, I have not taken in disturbance RAM. There is no disturbance. So when in no fault condition and no disturbance condition, what is my YT? YT is equals to C into XT. Fine, C into XT. Then let me do the derivative here. If I do the derivative, so derivative, what I'm getting it here, this is a Y dot T, that is equals to C into X dot T. I'll do little bit of mathematics, little bit. And these, whatever I'll do, will be understood by all of you. No issue. So I'm just replacing what is X dot. After replacing C X dot, so what I'm getting is CA, I replace it from here. Then I'm getting it CAXT plus of CBUT. Fine. If I do differential time derivative again on this Y dot, what I'm getting is Y double dot. This Y double dot is equals to CA, here it is X dot, CA X dot plus of CB U dot T. Right. So I replace your X dot T in this expression, then I'm getting CA square XT plus CABUT plus CB U dot T. Right. So this series will continue the moment I go on doing my integration, differentiation. All right. Continue. Now let me try to write it in a vector matrix form. So I have taken this y dot y double dot, see y dot y double dot, dot 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 up to mu derivative. up to mu at derivative. So what I'm getting it here, cxt, so that c has come here, caxt, so this is ca into xt, ca square. So if I continue this way, what I'll get it here, this term will be, see it here, ca square when you are doing double derivative, ca when you have done the double single derivative. So it will be your c of a into a to the power of mu, the mu at derivative into xt. And rest of the terms, once you put them in a matrix form, this will be something like this. First row is all 0 multiplied by u dot, u double dot up to u mu at derivative. Fine. Now, some of you, I don't know if you're observing it very carefully, you may immediately ask me a question, why we require up to mu at derivative of u? Because once you have done y double dot, see in the y double dot, what you have, it's u dot. So one derivative short of what is the highest derivative in y? What y? But I have simply mathematically extended, as you see it here, last column is all 0. Last column is all 0. And so that, and why I have done it? I have done it because, this vector has a length up to mu. This vector has a length up to, this is also mu plus 1, this is also mu plus 1. So therefore, length of the vector, I can put some name here. So for the generalization, this is something that has been done. Okay. Now, if you just substitute this, the CB, so first row is all 0 because y equals to cx plus, there is no term of u. Next, we have got caxt cbut, all right? So I have got cb term, rest all are 0. Here I have got cabut, so it's a cab, cbu dot, cbu rest all. So this way I will get this matrix here. All right, we'll get this matrix here. I hope out of this is something which is known to us. Can any of you tell me what is this matrix? This matrix is known to us.
Controllability, observability matrix.
Observability matrix. So good. Observability matrix. So what is the difference? Suppose your CA pair is observable. Right? So what will be the rank of this matrix?
Full n.
So the n. Fine. Now see, here I have not kept it and thought that for observability matrix, our derivative is up to c a to the power of n minus 1. Correct? For our observability matrix, we go up to c a to the power of n minus 1. All right. Am I correct?
Yeah, correct.
Correct. So because c a to the power n is linearly dependent on c to the a to the power of n minus 1, n minus 2, and so on by Cayley-Hamilton theorem. Right. Here what I have done, I have taken it up to mu. So I will increase this one up to any number of row I will create it here. Why I will create, I will show you. Okay. Now see what I want. I want a relation between inputs and outputs. I want a relation between inputs and output. Fine. Which will be equal to 0 in a normal situation, a fault-free situation. All right. Just a minute. In a fault-free situation. Okay. So if you look at this structure, if you look at this structure, see these involve y dot, y double dot. So this is something y is available to me. So therefore, I can derive all these derivatives. U is available to me, so I can derive all these derivative of U. Fine. And whatever coefficients I require, these coefficients are known to me. But what is my problem? My problem is I do not know this xt. For my plant, what is known to me is the input and output. This is known to me. I do not know this. So therefore, what I will now do, I will try to multiply by any vector, pre-multiply it by any vector, so that that vector multiplied by this matrix, which is similar to our observability matrix, that becomes 0. In fact, this term becomes 0. That particular, that vector multiplied by this into x2, that should be equal to 0. If this is so, then what I'm getting a relation involving this y and its derivative, involving u and its derivative. That relation is said to be an redundancy relation. Fine. Let us see. So therefore, if I use some notation to represent, so this is y, this is my c mu xt, and this one is some curly b I'm using. Fine. So this is my b into ut, and this is my y, and this is my c mu. Fine. So what we are now saying, that you have to find out parity space. So how you find the parity space? This parity space are found by finding these vector omega mu transpose, such that this omega mu transpose into c mu, this is equals to 0. So I go back and show you again. My problem was with xt. So therefore, I will multiply it by some vector, so that these vector multiplied by this, that is equals to 0. Fine. So what that will give you? That will give you that vector multiplied by this minus that vector multiplied by this, that is equals to 0. So that will give you this y minus bu, this will be equals to this, and which is equals to 0, because fine.
So is
Now,
the mu is less than
tell me again.
Is mu is less than n?
Is more than n. Is less than, more than n. See, up to n, it all depends on, I have to create number of row, how many such vector I require. How many such
So
vector I require.
you require some vector in the null space of your that matrix.
Very
So
correct.
that
Very correct.
the null
Very
space should
correct.
exist. That's what I'm thinking.
Yes, exactly. You got the point. You got the point. So basically, what is my problem here? My problem here, that I need to find out the null space of C mu transpose. I need to find the null space of so this is the null space of C. Sorry. So this is your null space of C mu transpose. This is what I need to find, right? This is what I need to find. Okay. So therefore, I basically, that put number of columns here, so that I get some solution of this null matrix. So what is that? What is this I'm doing? I have got C mu transpose into omega mu. This is equals to 0. Now the C mu, what happen is it will increase columns. So this is equals to 0. Okay. now I just that what I have taken an example, so that we understand what kind of relation that we get. Right. So if I take my A matrix is this, B matrix is this, and C matrix is this, and if we calculate this, that CA, if you calculate this one, because C is one dimensional, only one output, so I am getting CA is again only one. This is your CA square. This is your CA cube. I have taken this one and then I have calculated the null space of this one. Then null space has come out to be this one, right? So this omega transpose, omega mu transpose into this would be equals to 0. Okay. Now, if I calculate that omega mu transpose into this, if I do this one, see, you are getting this relation. You are getting this relation. You are getting this relation. Fine. So how you are getting? I will show you this way, that you are doing something what you call residual generation. So you have to generate the residual. What is this residual? Residual is equals to omega mu transpose into y minus of BUT, and this is equals to 0 in an ideal environment. What is that ideal environment? We have said no fault, but noise and disturbance, they must be present. I have ignored those noise and disturbances also, right? So in an ideal situation, if I generate a relation involving y and its derivative, u and its derivative, and if I do this, then I will get a complicated equation. This is equals to 0 in an ideal situation. Now, if I increase the value of mu, for example, it's I was doing suppose CA square CA cubes. Instead of that, if I go to CA to the power of 4, then I solve it, then I will get, instead of one vector, I will get 2 vector in the null space. Fine. So therefore, I will have 2 such relation here, and so on, and so on. 2 such. Now, in practical situation, that is, in practical situation, in the absence of any fault is not there. But in a practical situation, this residual will definitely not be equals to 0. It will have some value. So therefore, this RT we take as a threshold of residual. So it's a residual threshold. Right? So we define something called RT. So what is this RT? This RT should be less than or RTH, threshold value of R. Now, how do you select it? These RTH should be small enough so that whenever there is a fault, this will not be 0, this will become non-zero. This fault component will add here, fine, it will become non-zero. But it should be large enough, this RT should be large enough so that whatever value this RT is getting because of noise and disturbances, it should be more than that. Fine. So this is how I will choose it, RTH. Right. Now, there are a lot of research that has gone here. People talk about something called adaptive threshold, and there are so many other things, even on the choice of threshold, because it is very important in a sense that if you take it too low, what will happen? It is more than threshold, but not because of fault, but because of disturbances. So you are getting false alarm. Right? Now you have taken such a value you have taken such a value to take care of your noise and disturbances. There was a fault, but because of that fault, the way it has impacted residual, the residual value was less. So it is called, misdetection of your fault. You could not able to detect that particular fault. So it is so, you have to do some kind of design, some kind of things. Okay. Now, this relation, whatever you have written it here, this relation is called a parity relation. I hope, I don't know if any of you can, relate these, but it is a relation after all. It's a relation between input, output, and the derivatives. That's fine. But why we are bringing the term parity here? Can any of you tell me why the term parity? Anyway, have you we say some bit, we call it parity bit. Any of you definitely have heard the word parity bit when you, okay. So basically, during communication, when you communicate, you send a parity bit also to understand whatever you have sent, it has been received correctly or not. So it basically check your correctness. So similarly, a possibly parity word has been higher from that. So you got a parity. Okay. So this is what is called parity relation. Now, what is the issue here? What is the issue here? Issue in the parity generation from C mu. So what we have done, we have calculated your parity space by solving this equation, correct? By solving this equation. Fine. Now, what is the issue here? Can any of you see whether there could be any issue here? Or if we go a little more technicality, can you tell me whether it is a sufficient condition, it is a necessary condition, or it is a necessary and sufficient condition? Fine. Tell me. I wanted this to be equals to 0. I wanted this to be equals to 0, correct? Omega transpose, omega mu transpose, C mu, xt equals to 0. I never wanted omega mu transpose C mu equals to 0. Fine. This is something that I've done. So therefore, tell me, this is sufficient condition, this is necessary condition, or this is necessary and sufficient condition. Okay. Anyone? This is sufficient condition. Fine. This is sufficient condition. This is sufficient condition because the moment I make this is equals to 0, then the whole term will become 0 because 0 multiplied by anything equals to 0. Right? 0. Now, there are two issues that we need to understand. All right. What are two issues? First issue, this was not our problem. Our problem was this. Our problem was this one is our problem. Correct? This was our problem. What is the next thing? Next thing is that this C mu, it got generated from AC pair. But this AC pair, these will vary. If there are 25% here in this online meeting now, if there is a question, plant is given to us, we are asked to find the state space representation, there may be 5-10 different state space representation. So therefore, there will be 5 or 10 AC pair. So omega mu that you generate will not be same as what I generate, right? Because AC pair are different. Fine. So therefore, whatever I am saying it here, these are all from my thesis. Fine. My basically PhD thesis was these only. Fine. On fault detection, diagnosis, and dynamical systems, which I submitted to IIT Kharagpur way back in 1997. Fine. So what we have done in every book, still you will find this one only. This one only. Fine. But what we have done a necessary and sufficient condition for the parity relation. Fine. And what we have shown that if you are dealing with an ABC pair and if your AB is uncontrollable, then this particular relation will not hold. Fine. That also we have shown. Okay. Now, what is our contribution? Our contribution was a necessary and sufficient condition for the parity relation, and that too based on input-output model, right? Based on input-output model. Fine. Okay. Now, what we have done is after a lot of mathematics, we finally have come to this, that it's not omega mu transpose C mu, rather it is omega mu transport into H mu. What is this H mu? What is this H mu? H mu is like this. Now I have this transfer function matrix. These transfer function matrix can be represented in the form that Hi into s to the power of minus I, and I is varying from 1 to infinity. What you call to the Hi? Any of you?
I think it's a Taylor series expansion, a power series expansion, sir.
Power series, and what you call to this Hi? These are your Markov parameters.
Yes, sir. Yes, sir. And
These are your Markov parameters, right?
yeah, it is positive power of yes, maybe time movements like that, sir.
So these you can write in this way also: C into a to the power of I minus 1 into B, and I is varying from 1, 2. So this Hi is from your input-output model, and these C, A, B are from your state space model. Fine. So, so after all these derivation, what we have done, we have shown that this H mu, which is equals to H1, H2, Hn, H2, H3, H of n plus 1, then you have H of mu plus 1, H of mu plus n. So this is what H mu. And what you can show that H of mu is nothing but C a to the power of mu, this multiplied by B AB dot 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 a to the power of n minus 1. This is your, what you call to this matrix? BAB dot 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 a to the power of n minus 1b.
Controllable matrix, sir.
So this is your controllable matrix. Fine. This is your controllable matrix. Now, what happened is when see, when you do it from here, when you do it using this input output notion, what we have said that this is a necessary and sufficient condition. For the same example, what happened is if you calculate your parity space, the parity space comes out something like this. Now, if you calculate this into C mu, this is not equals to 0. But if you do omega 2 C mu into xt, then that is equals to 0. Fine. So these alone made it sufficient, but this is something which is necessary and sufficient. Okay. Fine. So now let us go to the next approach. What is your observer-based approach? Now, in this observer-based approach, what we will do, I'm just showing you the initial part, what we basically do. We have to generate a residual. So how you generate your residual? Your residual you generate is output that's coming from the plant, and this is your output which you have generated using your estimated output, using your observer. Now, what should be this value of RT? All those discussion hold here also. This is equal to 0 in an ideal situation, but this RT should be less than RTH for a practical situation. Fine. Now, this is a disturbance term. So we have our standard Leuenberger observer, L into y minus of y hat, and y hat is equals to c into xt. Then our residual is this. Fine. Okay. Now, there are so many different types of, fault detection observers are being reported in the literature. Fine. Now, what I'm talking about something when I did it, maybe during 95, 96, during those days. Not only the simple Leuenberger observer was there, but also there were many others. So what I have done, what was our contribution? Our contribution was that are they all isolated? For example, Leuenberger observer, the way you design your fault detection and diagnosis observer, is it completely different from if you do it something called eigenstructure assignment fault detection observer? If you do something called unknown input fault detection observer, if you use something called factorization approach and some more, I have just for the sake of the simplicity, I have taken few. Fine. Now, what we have done, we have tried to see that are there any similarity in their approaches or they are all completely different. Then what we have understood that the all fault detections observers are something like this. These fault detection observers are, this is our y minus gs into u. Fine. Y minus gs into u. Ideally, this will be equal to 0. Fine. This is something which is passing through a error filter. This is something which is passing through an error filter. Now, what we have done after doing lot of manipulation, then we could able to find that all these approaches vary how you have designed your WS. Fine, WS. So for example, for Leuenberger observer, your WS happens to be something like this. Your WS happens to be something like this. Identity matrix minus of C into SI minus A plus LC inverse into L. Right? Now, when you do the eigenstructure assignment, so we do the eigenvalue, pole placement that we do. Fine. So here what happened in eigenstructure, you place both eigenvalue as well as eigenvector. So this is what is called eigenstructure assignment. So when you do eigenstructure assignment, this WS comes out to be something like this. This comes out to be something like this. Okay. So it is a Leuenberger observer, whatever filter we had for the Leuenberger observer, that and then multiplied by a constant matrix W. A constant matrix W. So what is this constant matrix W? This constant matrix W basically derived from this expression. Derived from this expression. Right? Derived from this expression. Right? Now, okay. Now, in terms of vector, null vector, we can all talk about what is this, how do you find out your W? Let us skip that. Fine. Now, there is another fault detection diagnosis observer that is called unknown input fault detection observer. So it basically annihilate your what you call disturbances and then, okay. Now, here your WS comes out to be something like this. It's a reduced order observer. They are full order observer. This is reduced order observer. So this is something like L1 into SI minus of AF inverse G plus of L3. Right? Now, these all L1, AF is basically the closed loop observer matrix A minus LC. Fine. And this L1, G, L3, they all has got its meaning. I have not brought those meaning here just for simplicity. I'm just trying to show that whenever you will be using any kind of fault detection observer for this purpose, then you should just keep in mind that this is something you are designing another WS, right? Another WS. So before you design another WS, you should also see what are different WS already exist in the market. What we have next is a factorization approach. In this factorization approach, as you see it here, this is your WS is equals to RS into DS. RS into DS. Now, what is this DS? DS is equals to, you have GS, you have done a factorization. So you have done a factorization of the GS. This is equals to D inverse of S into NOS. So you have done a co-prime factorization, and RS is a suitable matrix to satisfy other design conditions. Okay. So what I have tried to show it here, that in that observer design, what is being done, we just use different approaches just to design different WS. Right? This is what you do. Now, going ahead, you have got parameter estimation based approach. What you do it here, I'll just take a series. Now I have taken a model here just for our exam, for our understanding. I have just taken a simple a third order model. So this is our model, and our model parameters are this A1, A2, A3, B1, B2, B3. They are the model parameter, right? Now we do our estimation, parameter estimation algorithms are there. So there are so many different type of algorithms. By using those algorithms, we will try to estimate the values of A1 hat, A2 hat, they are all estimated parameter, A3 hat, and so on, right? Estimated parameter. Now, how do you define your residual? You define your residual as R1, first residual is actual value of A1 parameter minus estimated value of model parameter. Similarly, you have A2 minus of A2 hat and so on. So you have got all these parameters, right? So if you concurrently run this particular parameter estimation algorithm, and if you do the subtraction to find out what is the value of residual, as usual, this residual should be, all this residual Ri, this should be less than some RTH. This should be less than some RTH. Fine, when there is no fault. But the moment there is a fault, so there will be a variation of this. So Ri will no longer violate this particular clause. So what we have done, if I do parameter estimation and compare with its true value that is known to us, we will immediately come to know that there is a fault in the system. Not only that, we will also come to know that which are the model parameter that got affected. Fine. Say, for example, it may happen that R1 is more than RTH. And also, suppose R5 is more than RTH. I'm just doing it arbitrarily, right? So what it says that two parameter, that this model parameter, there is a problem with this model parameter and there is a problem with this model parameter. So these two model parameter has problem, right? Now you need to do diagnosis. You need to do isolation. So therefore, these model parameter may not give you the clue that which are these physical parameters. So therefore, what you need to do is you need to basically find out which are the physical parameters which are responsible for this model parameter to vary. Fine. So if I write it this way, that I have the model parameter which are function of my physical parameter, right? This is not only a nonlinear function, it's a very complex function. Whatever examples I have done, in most of the cases I have found this is a very complex function. So therefore, what is our problem? Our problem is to find, this is a small f. So our problem is to find the process parameter. So from the process parameter, we have to find the inverse mapping. We have to find this inverse mapping from the model parameter. So once we can find out these kind of inverse mapping, then that will give me what are the values of your physical parameters. I hope you are understanding the difference between physical parameter and model parameter. Fine. For example, our standard second order equation, we have s square plus of twice of zeta omega n is plus of omega n square. Fine. So all these together, they give me the model parameter, but zeta and omega n, these are the two physical parameters. Fine. So therefore, you understand in a plan, there will be so many physical parameters, and those physical parameters in some combination appears in your model that you have represented. Fine. That is your model parameter. Okay. Now, fault accommodation. What we understood, that there is a fault in the system. We accept that fault and then we reconfigure, we do something so that my system runs at least in some optimal mode. Right? Now, what I'll do it here, I have just taken some case studies from our country. So this will not only show that how fault accommodation is done, but also it will establish that why this is must in today's industrial automation. Right? Let us try to. So first example is thermal power plant failure Fine, NTPC Dadri, Uttar Pradesh. What had happened here in 2019, 210 megawatt turbine experienced a bearing fault. Fine, due to vibration anomalies. Fine, risking a full unit shutdown. All right, this is what they have detected. Okay. The vibration sensor detected the fault via real-time monitoring. Diagnosis used model-based residual analysis to isolate the bearing issue. So therefore, here vibration sensors are used. So this is again a data type. A model-based analysis is also done to find out, to isolate the bearing issues that it had happened in the bearing. Fine. So what I'm trying to emphasize, if you note that here I'm showing you, look, both database and model-based have been used. So they are going for some kind of hybrid motion. Accommodation involves switching to redundant cooling pump and adjusting turbine speed control, maintaining 70% output for 48 hours until repair. So this is a condition that they have made. What they have made, they have now run their plant at suboptimal condition for 48 hours until that repairing is done. Fine. What they have said, that this has prevented them a 40 crore loss from downtime. Otherwise, as it's been said, risking a full unit shutdown. Fine. So they run that plant and they have saved at 50 crore from here. Right. Let us see the next one. This is in Tata Steel Jamshedpur. Fine. Steel mill induction motor. What happened? This is a case in 2022. This is a case in 2022. So induction motor in hot strip mill developed an electrical fault from insulation degradation, threatening rolling operation. Fine. Now, thermal imaging and current signature analysis detected overheating. Diagnosis pinpointed winding issues. Accommodation activated a redundant motor drive and reconfigured a PLC to redistribute load and sustaining a production at 85% capacity. So therefore, they have used a redundant. So what you call to it, this is a passive type of redundancy. So they were not using this particular motor there. Fine. So they have activated once they have got that fault. Okay. Next, you have an Ultratech Cement Gujarat. That case, cement clean process fault. In 2021, a clean in Magdala plant faced a refractory lining fault, causing temperature spike and potential clinker quality degradation. How they have detected it? Acoustic emission sensors. This is again a database. Flag cracks. Model-based simulation diagnosed thermal stress. Accommodation rerouted fuel flow to auxiliary burner and engaged backup preheater, stabilizing operations without halting the clean. So this is their accommodations, what they have done. Now, what is their benefit? Avoided a 24 hours outage costing 2 crores. So they have saved 2 crores by this. All right. Power grid transmission line fault, fine, in a northern grid. 2010 to Delhi blackout precursor involved 765 kilovolt line fault from insulator flashover during monsoon overload. Your phasor measurement unit detected voltage sag in real time, diagnosed via impedance-based isolation, Accommodation used redundant lines for load transfer and dynamic line rating adjustment, restoring balance in 10 minutes. So what they have done by doing all this, mitigated a potential nationwide cascade. Fine. My last one is here. So this is your pharmaceutical mixer fault. In 2023, a high shear mixture in API production line suffered a gearbox fault from misalignment, risking batch contamination. So whole batch will get contaminated because of that gear fault. Fine. That is the loss. What they have done, first, what is their monitoring system? So this is vibration and acoustic monitoring, identify anomalies, knowledge-based rules diagnose gear wear, accommodation switch to a standard mixer, and recalibrated speed via adaptive control, completing the batch seamlessly. So this has ensured manufacturing process compliances and avoided 1 crore in rework. Otherwise, they would have done. So this is what is the scenario of industry today. So therefore, those who feel that you can do something in theory, please note that there are many industry who will be your taker if you have a better algorithm than the available one. Okay, now coming to conclusion and take home. So what is the concluding remarks? Fault detection, diagnosis, and accommodation is must in today's complex processes. Fine, this is must. Now for life critical processes, aeroplane, airspace, this is, that shuttle space, and also nuclear power plant, or for example, petrochemical, some of them at least, life critical processes, physical hardware redundancy may be used. And in other processes, analytical redundancy may be implemented. Fine. Now, in analytical redundancy, what we have seen today, model-based. In model-based, what we have seen today, that there is something called parity approach, parity space approach. There is something called observer-based approach. There is something called parameter estimation-based approach. There are many others. Data-based, you take the data and then you do some statistical analysis. You use some machine learning. You use some AI tools, and then you try to find whether they are normal data or they are coming from some faulty section. If they are faulty, then these represent what type of fault, right? And then we have knowledge-based and hybrid approaches. From the real life examples, what we have seen that current trend is an hybrid approaches where you take advantages of all approaches. Now, things what need to be noted is every approaches has its own advantages, has its own disadvantages. For example, if you do model-based, then you will not be able to, that identify any unknown faults. But if you go for database, then unknown faults. Right. Now, final note is the use of fault detection, diagnosis, and accommodations has been increasing with hybrid approaches. Fine. Now, before I conclude, these are my bibliography. I have not cited anything. Therefore, I have put this bibliography. So first one is my PhD thesis, design of residual generator for fault detection diagnosis in continuous time dynamic system, right? I have taken, as I said, we teach this particular, rather I teach this particular subject here at NIT Silchar. So I mainly refer to these two books, Fault Diagnosis in Dynamical System, Theory and Application, Patton, Frank and Clark, Prentice also of India. and then fault diagnosis system and introduction from fault detection to fault tolerance by Iserman. This is mainly on parameter estimation approach. Now, before I conclude, let me take 1 minute time. Basically, you know that what we are doing here, you know, we have data, and these data represent my normal system. Fine. So therefore, what I have done, I have basically any model, my CNN model, this model, NN model, some model. Fine. So this is not mathematical model. Fine. This is a non-mathematical model. So I have giving these data here as an input. Fine. And I'm getting the response. It is faulty, or it is a faulty system or unfaulty system. Now what happened? Theoretically, I generate data, faulty data. Theoretically, I generate faulty data for different kind of fault. Say, let me write it this way, ith faulty data. So this is ith type of fault I have created, and I have taken the data. What I have done now, I have one more model. This model represent my ith model, ith fault model, ith fault model, right? Okay. So what I'm now doing, now I am comparing these outputs. Here I am getting, say, I is varying from 1 to n. So in different type of faults I have, this is my normal system, and this is my actual plant. So I'm getting data from the plant, output from the plant. Fine. Right. So these all I'm comparing. So what will happen? What is expected that there may be fault of one type at a time. So out of this, if there is a fault, this will say that there is a fault because it will deviate, and this will say which fault has occurred, because I minus 1th model will show that they are matching, but that ith fault will show that response is 0. Ith model will show their response is their summation from these and action input, they are 0. Rest all will show us non-zero. That will tell me that there is a fault of ith type. So this is the general notion which is used in database, which is used in observer-based, which is used in everywhere. Fine. So this is how basically they diagnose this fault. Okay. So let me thank you for giving me this opportunity, and all of you, those who have interacted with me, those who have not interacted, if you have any questions, it will be so nice that you may drop your questions, or any queries, you may drop your queries, and here is my contact. It will be so great. Fine. So with this, let me end it here. With thanks.
Hello.
Any questions you have, you can ask me. Yes.
Yeah. Is there any application of this thing in power system? Because this.
Yeah. See, power system, I have shown you one. No? In fact, what had happened after that blackout, when in 2012, we had got only one PMU. Fine. Now we have got hundreds of PMU, and these PMUs are giving me this is the real-time data, real-time information. Fine. That examples which I have shown you, in Delhi 2020. There are many. See it here. And what they have claimed, because of this system that they have, fine, they could able to mitigate a potential nationwide cascading effect of this fault. This happened in 2020. But they restored just in 10 minutes. They restored just in 10 minutes. Fine. Transformer, a primary component, fine. So many work, even my works are there. So many works people has done, for finding the fault in this transformer.
Yeah,
Fine.
sir, I have done one work during my MTech. It's using Lyapunov index for detecting the voltage stability, but it actually didn't work much.
Lyapunov index for detecting.
Yeah, voltage stability, actually instability occurs when you have that the saddle node point. But saddle node, yeah, we are actually assuming that it is, we are actually assuming that it should be, there should be some kind of chaos during that in during the saddle node point. When the saddle node point has happened, then you will have some kind of chaotic behavior of the voltage. But it actually didn't match properly the Lyapunov that thing, Lyapunov exponent.
Actually, see what happened. One of my MTech student, he tried something, chaos in power system. But what we have found, that we can theoretically generate, by varying some parameter here and there, some chaotic phenomena. But in actual power system, such chaotic phenomena are very rare. In a sense, whenever there is a disturbance, there are so many absorber there, so it immediately absorbs. So for a chaotic system, what happened? Your response is a long-term aperiodic response. Fine. It runs for hours and hours, days and days. That is your impact of chaos. That kind of situation not happens theoretically, but practically. So even I don't know, I don't remember. Maybe my students also submitted paper, or maybe he has something in his credit. Fine. Theoretically, we can show something. But what we are talking about, Lyapunov exponent will tell me, Lyapunov exponent will tell me the current condition of the system. If all the Lyapunov exponents are negative, it tells me that system is stable now. If first one, L1 is 0, rest are minus, so it has gone to a periodic motion or a limit cycle. Fine. If first one is positive, second is 0, rest are minus, then it will say it's a chaotic system. If first two or more than two are positive, 1, 0, rest are minus, then it will say hyperchaotic. So this much information we will get from the Lyapunov exponent. Fine. Maybe you are doing something. If you write back to me, possibly we can see that problem, why it did not work, or whether at all it should work. Fine. So we can take up that issue. Any other questions any of you have?
Yes, so participants, if you are having any questions, so please you may ask from sir. So, sir, I think no one is having any doubts, sir. So, I extend my sincere thanks for delivering such insightful and engaging expert talk. Your valuable time, effort, and expertise greatly enriched the session and provided the participant with deep knowledge and inspiration in the field of fault detection and accommodation techniques for the dynamical systems. Despite your busy schedule, sir, you graciously spared your valuable time to be with us. I truly appreciate your contribution to making this event a great success. I look forward to your continued association and will be delighted to invite you again as an expert in our future events. So thank you so much, sir. So now we are going to start our validatory session, sir. So please be.
I should also thank you, Arvind, for giving me this opportunity to interact with all of them. Fine, I do not know how much I could able to convey, but then I try to give you a glimpse of, it's a glimpse of what is this. And in such interaction, simply that is something that we can, as I said, if any of you are interested, of any of you have any questions, any doubt, anything you wish to discuss, you can write to me. Thank you. Thank you, Arvind.
Yeah, thank you, sir. So now I would like to other organizers, Dr. Neeraj, sir. So please start our validation, sir. So thank you so much, sir.
Yeah. Yeah, everyone, thank you. Yes, you started.
Yeah,
Let
Neeraj.
me-
Thank you, Dr. Arvind.
Yeah, thank you, sir.
Am I audible?
Sir, you are audible, sir.
Yes, sir.
Yes.
Yes, sir. Please, sir.
So I hope, sir, head of the department has joined. Nitin, sir.
No, probably he's not here, I think.
Okay. So shall we wait, sir, or shall we proceed?
So just a minute. He just joining, sir.
Okay.